So we have learned about several concentration results. One of the simplest was the Chernobyl, right? So we have, in Chernobyl, we have like x1 to xn. Each of them are, either 0 or 1 with a certain probability. And they are independent. And we want to we want to give the concentration result on summation of this. And for example, if we want to compute the number of H's in G and P, then you sum all Ij, which is a pair in bracket n, and we consider the indicator random variable whether this Ij belongs to the random graph or not. So Chernobyl inequality gives you concentration. But consider it, now you want to consider the number of triangles in random graph. Then what you have to consider is you consider indicator random variable with Ij, Ik, Jk, and you multiply them. Ijk, where Ijk is the triple. So you want to now bound this. So you want to estimate this. So before there are independent random variable and then you just add them, then you can use Chernobyl. But this is something different. So this is a setup that you have an independent random variable and you consider a polynomial of them. So before, the polynomial is a polynomial with degree 1, but this is more complicated polynomial. So one might ask that is there any stronger result which can be applied to this kind of polynomial? So there is this result called Kim-Bu polynomial concentration. Here Bu is Bamboo and Kim is Jung-Han Kim, who is in KAIST now. So one thing is that so we want to consider this kind of polynomial. But in here, if you say again, if you take some power here, because this is indicator random variable, this is not different from the original indicator random variable itself. So this is our polynomial, and we can, because of this reason, we can consider only multilinear polynomial whose monomials have is a multiplication of distinct variables, whereas each variable has a power only 1. So let's consider the following setup. So this polynomial can be actually written in a slightly different form. So it's the same thing, but we can actually consider this as a language of hypergraph over variables. So let H be a hypergraph. Again, hypergraph is collection of sets. And for each E, which is an edge of this hypergraph, we consider its weight to be some non-negative number. And we consider T1 to T, let's write it this way, Ti, where I is the vertex. For each vertex, we consider indicator random variable, which are mutually independent. So this is a variable taking value 0 or 1, where say it is 1 with probability pi. And now we want to consider y as for each h is in this hypergraph, we multiply the random variable inside of this h, and we put this coefficient. So for example, if y is 2 times x, t1, t2, t3 plus 7 times t1, t4, t6 plus t2, t3, t5, then our h is, you have 1, 2, 3, 4, 5, 6. You have this h 1, 2, 3, and this h 1, 4, 6, and this h 2, 3, 5, with the corresponding weights. So, and we actually allow empty set in here, then we consider this as a constant. So, I mean, we might want to consider the polynomial which might contain constant, so we consider this setup as well. So now what we want to consider is that some of them are 1, some of them are going to be 0, right? So we let S be a random vertex set which is obtained by adding each I to S independently at random with probability pi. So S can be considered as a collection of random variable which has value 1. So we have these random variable, and you, do the experiment. Some of them has value 1, some of them has value 0. The ones with value 1 forms this set S. So that's one way of thinking it, or you can just consider this random set, and then you, every, random variable which belongs to this random set has value 1, and outside has value 0. You can also consider it this way. And for this, now we consider a subset. Let's say that K be an upper bound on the, let's say that this hypergraph has n vertices, and K be the size of largest edges. So our hypergraph does not have to be uniform. The polynomial could be non-homogeneous, so it's not uniform. Then y is same as the weighted number of hyper edges in induced subhypergraph. So we have H, we have this vertex at S, and we consider all the edges lying inside of S. And we count them. We count them with weight. So H with weight 2 is counted twice. H with weight 1 is counted once. H with weight 1.5 is counted 1.5. Then such counting is same as y, has the same distribution as y. So now we can consider in this setup, and we will define one more concept which will be useful. This is in analogy with the link graph. So what we do is we have hypergraph with the hyper edges. So let's say we have A here. What we do is we consider all the edges which contains A, and then we consider E minus A, E prime minus A, E double prime minus A. So for each edge, you just delete A. Then that gives you a new hypergraph. And that hypergraph also corresponds to a polynomial. So that's y sub A. So for those terms with E containing A, what we do is we set Ti equal 1 for all I inside of A, meaning that we replace this term by the multiplication of this outside of A. So all the things inside of A, we just plug in 1 to the parameter, to the random variable. While all other term which corresponding to E, which does not contain A, are disappeared. So which is exactly as I described in the hypergraph. You'd have a set A, and you consider all the edges containing them, and for each of edge you just delete this A, then remaining thing you just consider the remaining edges. And for those edges which does not contain A, you just delete them. This is actually same as partial derivative of y with respect to all Ti where I is in A. And now we write E sub A to be the expectation of this YA, and E sub I be the maximum EA, where A is a set of size I, and let mu be the expectation of Y, and let E prime be the maximum EI for all, I, among all I between 1 and K, and let E be the maximum of mu or E prime. Then, Kimbo polynomial concentration says that with the above setup, and let's say AK is some number depending on K, which is not so important. TK is also some number. Then for any lambda bigger than 1, we have that the probability that Y is far from its expectation, which is measured by this E and E prime times lambda k, is small. How small is exponentially small. in terms of this lambda. So in application, we will make sure that this lambda is at least polynomial in N. And this is exponential term, and this is only polynomial. So this decreases much faster than this. And this is polynomial, and this is polynomial. So we make sure that this is smaller than mu to show that y is concentrated around mu. We will not prove this theorem, but if you consider some, intuition, let's say we have this A. So before, in the concentration results like Azuma or other things, the Lipschitz condition was one of the important thing, right? If you change, so you have many coordinates, so many independent random variables, or it doesn't have to be independent, but many random variables. And if you change one, then we wish that not much is changed. If changing one can cause a lot of difference, then it's not good for us. So changing one, we want to make sure that it doesn't cause too much trouble. Here, watch this EA. EA is roughly, intuitively, what EA is that if you make some changes inside of this A, then how much in expectation, this is expectation of YA. So you keep everything outside, or you let everything outside as a random. But if you determine A somehow, determine the values inside of A somehow, and you change those, then how much change we get is roughly this EA. So that's the rough meaning of this. So everything outside is not exposed. So we want to, change the expectation of Y, assuming we know of A, xi, for all here. Roughly, so what we wanted to show is that Ti is xi, Ti is x prime I. So we want to make sure that these are not big. And that's roughly encoded if we make sure that this EA is not big. Sorry, give me a moment. So that's a rough intuition why we care about this E and E prime. So you have this term. So if this E prime gets bigger, then our concentration gets not so good. And if it gets smaller, then our concentration gets better. So we will not prove this theorem, but let's consider one application. Application on the number of triangles containing specific vertex x. So let's say P is n to the minus alpha, with alpha being between 0 and 2/3. Then we fix the vertex x of G, which is drawn from the random graph G and P. And we let Y be the number of triangles containing x. Then, and let U be the expectation of Y, and expectation of Y is roughly this. You can consider this. So you have x and you choose two vertices Y and G. Then probability that this is an H, this is an H, this is an H is P cube. So P cube, so choosing this is n minus 1 choose 2. So roughly this is that. Then let's say there exists epsilon, which is depending on alpha, such that we have for delta, there exists, say, C delta, such that the y is far from, the difference between y and mu is more than delta mu, is at most exponentially small in here. Let's multiply C delta here. So this means that the y is concentrated around the mean with the exponentially high probability, or minus exponentially small function. So again, we consider indicator random variable Tij, which is indicator function, whether this ij is a h in G or not. Then y is summation of all, you consider all the pairs outside of x, and this is y. So recall that in our setting, these pairs are vertices in our hypergraph. So in the previous setup, our BH is here pair, and H of H is the triple Ij and Jk, Ik. No, in here H's are, let me say, Xi, Xj, Ij, where Ij are two numbers not in X. This is a polynomial of degree 3. So now what we want to do, we want to measure this E prime and E. In order for that, we need to measure this EA and EI. So what A can be? A can be set of size, say 0, 1, 2, 3. And if A is empty, then E sub A is same as just mu. This is expectation of YA, but the YA is same as Y, so this is mu. If this is 1, the A could be, say, Xi or Ij. If this is Xi, X is here, I is here, we already know there is an H. Then we have to choose J by n minus 2 choices. And then the probability that this is H, this is an H is P squared. So expectation of YA. So again, YA is just you plug 1 to this Xi variable, and then remaining thing are determined by J, which is n minus 1 choice, n minus 2 choice. So n minus 2 times p squared, so roughly n p squared. And if this is ij, then there is only one term which contains ij. Then you have this 2, so the expectation is p squared, which is small. So we want to compute the maximum. So this is not even, we don't even have to consider. A could be xi, xj. So if size 2 is xi, xj or xi, ij. Those are the two cases. In this case, again, p. So ij is, we just have to check whether ij is an edge or not. The expectation is just p. In this case, again, p. If it has size 3, then, I mean, there is only one term, so this is 1. So out of this, and mu is n square p cube. And give me a moment, E prime let me check one thing. Yeah, okay. So now we can say that yeah, so 0 was actually not, we didn't have to consider. So E prime is a maximum of np square or 1. Say it's at most that. And now we have to compute E, which is maximum of E prime or mu. And mu is, we know, where was mu? This. So we have to consider mu is n to the 2 minus 3 epsilon half, but constant is not so important. And this is n to the 1 minus 2 epsilon. So we have to compare whether this is bigger or this is bigger. But we know that this is actually bigger than np square. So now what we want to do is, here we want to make sure that this is roughly some constant type mu, while lambda is some n to the epsilon. So lambda should be n to the some number. So we want this to be slightly smaller than mu. So this is mu times n to the minus epsilon. So we want to make sure that for some epsilon. So how do we do it? Is if alpha is smaller than half or alpha is bigger than or equal to half, then we let epsilon be 1 over 12, and we let epsilon be here 1 over 6 times 2 minus 3 alpha. Then what do we have? E prime is, so E prime is maximum of, what's this? That's mu under n to the 1 minus alpha, or 1. In this case, this 1 minus alpha is bigger than half, which is 6 times mu epsilon. So in that case, we know that this is some constant times mu times n minus 6 epsilon. It's bigger than that. And what's in this case? Alpha is bigger than half. Then mu is roughly n to the 2 minus 3 alpha. And here what we have is 1 minus 2 alpha. So this is n to the 1 minus 2 alpha. So n to the 1 minus 2 alpha is mu give me a moment. Oh yeah, we don't have to do this. And this is also at least 1, right? So 1 is at least mu times n to the minus 6 epsilon in this case. Because mu itself is n to the 2 minus 3 epsilon. And this is n to the minus 2 minus 3 epsilon. So this part is smaller than or equal to 1. So we have this. So yeah, not just this, but we can actually say that this is roughly same as this. Because if alpha is bigger than half, then this term dominates, then this term is roughly 1. And if alpha is smaller than half, then this term dominates. And because of our choice, I mean, this is also roughly this. Give me a moment. Let me mu over mu n to the 1 minus alpha. So let's do this. So epsilon is 1 over 6 times 1 minus alpha. Then, I mean, we can get this. We can actually check this. So now we use Kinbook polynomial concentration with lambda being C prime n to the epsilon with some C prime. So that which actually depending on delta. Then you just plug the numbers in here. Then what do we get here? Is we get the numbers as AK, E prime, half, lambda K, and K is here 3. And here what you have is mu, and mu times n to the minus 6 epsilon, half times here, lambda to the 3, so n to the epsilon. Then this is mu, and this is n to the minus 3 epsilon, n to the 3 epsilon, so this term goes away. So this is more or less mu, but we have this C prime. And C prime term, you just take a correct C prime so that the remaining constant multiplies to this delta. Then on the right hand side, you have this term. Again, we know this lambda, which is exponential of some constant depending on the delta times n to the epsilon. And this term is just a polynomial, so this dominates. So, I mean, by changing this constant a bit, so we can actually delete this term. Then we can actually prove this concentration on the number of triangles containing a given vertex. So this is one way of applying this. And more generally, you can consider number of, say, C6 containing 3 vertices, or more generally, you can consider some graph H which shares these specific vertices. So that can be, also prove that those numbers are concentrated around its mean by using Kimbu polynomial concentration.